Hey, what is that? Magnesium chloride. Look at how smart you all are. So we put magnesium chloride into water, and what does it do? It dissolves. What does it really mean when it dissolves? The water gets in between, and we actually call this process dissolution. And it means that the magnesium and the chloride ions are sort of free to go their own ways. And so what we have is no longer a chunk of magnesium chloride, but we have magnesium ions and chloride ions just kind of floating around. We call it dissolution. And lo and behold, we can write a formula for it, or an equation. So we can write this dissolution equation. Well, what if we also put in there, let's see, some sodium carbonate, Ne2CO3. Excuse me. So if we dissolve some sodium carbonate in there, we get 2Na1 plus aqueous. And we get some CO3 2 minus ions, also aqueous. So if we put magnesium chloride and sodium carbonate in together, can we predict if we're going to get a precipitate? And this is the part that this is where we left our chemistry heroes way back last week before all of the adventures that we've all had in the meantime. Okay, so those are our dissolution equations. If we want to know if we're going to form a precipitate, what do we do? This would be step 1. Step 2? Well, step 2, we go ahead and write a double replacement reaction between the magnesium chloride and the sodium carbonate. And you know how to predict the products that we would see. We would get magnesium carbonate, MgCO3, and we'd get sodium chloride, and of course to balance that we'd have to have 2 of those. Okay, so far so good. Now we know that the magnesium chloride and the sodium carbonate that we put in were all aqueous. Do we know about our products? What we have to do, of course, is look up their solubilities. So you need to get out the solubility table in your book. Okay, so you look it up, and you know that sodium chloride is soluble. You didn't even have to look that up. But if we do look it up, we note that Rule 1, most sodium compounds are soluble, and Rule 3, most chloride compounds are soluble. So yeah, we know that this is soluble. So the sodium and the chloride are going to stay in aqueous solution. What about magnesium carbonate? In fact, no, most carbonates are not soluble, and magnesium carbonate's no exception. So that is Rule 4. Most carbonates are not soluble, except those of sodium, potassium, ammonium. This is none of those. So we're actually going to see a precipitate of magnesium carbonate. Okay? Now what we need to do is write what's called the overall ionic equation. So the overall ionic equation takes all these things that are what we really actually threw in together. Because remember, these things are not really what we threw in together. Those are really the things that were dissolved. What we really threw in was sort of a soup of magnesium, chloride, sodium, and carbonate ions. So step 3, writing the overall ionic equation, takes a little bit of space. Yeah, it sure does. Here we go. I put in my reactants. What do I get as a product? Well, I get the sodium and the chloride ion, or the sodium and chloride ions are going to stay as they are. So I'm just going to copy these over. They're not going to do anything different. But the magnesium and carbonate, when they see one another across a crowded room, when their eyes meet, in fact, they will become locked in the embrace of an insoluble compound. And we get this precipitate of magnesium carbonate. That is our overall ionic equation. That shows every single thing that's in there, start to finish. Now step 4, and I'm going to move this stuff around a little bit. Step 4 is just to go through and cross out, and I've done it as a separate step. Very often it's done sort of in the same space as step 3, but I just did it. I copied it all over just to make it clear. Step 4 is crossing out what we call the spectator ions. So those spectator ions are the ones that are just standing around not participating. They are in the same form on the reactant side as they were on the product side. So if I cross out my spectator ions, who am I crossing out? Well, chloride and sodium aren't doing a darn thing. They're in the same form they were. They haven't changed forms. They haven't joined up with anybody. So that makes them spectators. So I'm going to move all of this up. And now step 5 is rewriting what's called my net ionic equation. So the net ionic equation is what's left after you've crossed out the spectators. Mg 2 plus aqueous plus CO3 2 minus aqueous yields Mg CO3 as a solid. That's my overall ionic equation. It's as though the sodium carbonate wasn't even there, because it's just a spectator. It doesn't change forms. It doesn't do anything. That is the process for writing a net ionic equation. We're going to do a quiz on this tomorrow when you walk in. Why are these useful? Well, the big place they're useful, I will tell you, is in neutralization reactions. So we're going to start to talk about, and we don't, unfortunately, we're not going to get into the acid and base chapter. I had hoped to, but we just aren't going to get there. Let's do one more, and I want to see if anything strikes you. Well, we'll come back in 4 minutes. What do I have? Name them. What's the first reactant here? Sodium hydroxide. Not very nice stuff. It tends to lie. I thought that was clever. So anyway, we got lye. It's a base. It is alkaline. It has a fairly high pH. You know, straight up lye is probably going to have a pH of what, 10, 10.5. What's the other stuff? Hydrochloric acid. Hydrogen chloride, yes. But we know HCl is hydrochloric acid. What happens when you mix an acid and a base together, both in aqueous solution? You've done this. You've mixed an acid and a base together. Probably not this acid and this base, but I could pretty well guarantee that you have mixed an acid and a base together. That was sodium hydroxide and a fatty acid. This is sodium hydroxide and hydrochloric acid, but you've probably mixed acetic acid and sodium bicarbonate, also known as vinegar and baking soda. Because what 7-year-old doesn't love mixing baking soda and vinegar because I can make bubbles and foam and a mess? Heck, I like doing it. So, what happens when you mix an acid and a base together? They react. There's a chemical reaction. And it's a very specific type of chemical reaction. So if you had to predict the products of a double replacement reaction with these two things, what would you predict? One is easy. Oh, you got the hard one. Okay, yes. So what we get out of this, and I think you guys did this as a double replacement, you get sodium chloride and you get water. And everything here, it's nice, it's all balanced because, well, everything's got a 1 charge. So, is sodium, well, we'll do that for good form, okay? So if we had to talk about sodium, if we're going to do the whole multi-step process here, where we dissociate the sodium hydroxide, we get NaOH in solid form, yields sodium 1 plus, hydroxide 1 minus ions, all aqueous. Is hydrochloric acid, is that an ionic compound? Oh. Well, then we need to talk about something else first. It's not an ionic compound. Hydrogen chloride is a molecular compound. It is covalently bound. It's two non-metals. And we know that when we have two nonmetals, they typically bond covalently. They're sharing electrons. So this is where we want to talk a little bit about how that differs than what we see when we have an ionic compound dissolved in water. Ionization. So ionization is a process that some molecular compounds go through where when you put them in water, they actually form ions. This is different than dissociation. Dissociation is what an ionic compound does. You throw sodium chloride into water, it's already made up of ions, they just get split apart. It's like losing your friend in a crowd. You're holding friends with your hand, you walk into a crowd, you get separated. That's dissociation. In ionization, so in ionization, I'm trying to think of a good analogy to walking into the crowd with your friend. Maybe you didn't have a friend to get separated from, and once you get into the crowd, you realize that that person over there is your friend. I don't know. Anyway, that's a terrible analogy. I'll work on it, I promise. But in ionization, they're already charged particles. They've just gotten separated from one another. In ionization, they are becoming charged particles. They're forming ions. HCl is a case of the latter. HCl ionizes. Okay, so knowing that, we know that what's going to happen to that HCl is the same thing that happened to the NaOH. We're going to get hydrogen ions, and we're going to get chloride ions in aqueous solution all, which means that the rest of our steps are pretty much the same. It looks more like a parentheses than a letter C. Let me fix that. Okay, so that would be our first step. I kind of did the second step out of order, but we can just copy this. What do you know about sodium chloride? We've said it enough times now. Oh, what do you know about sodium chloride? We've done this a bunch of times. It's still soluble. So that's going to remain an aqueous solution. What about water? What form do you think a bunch of water is going to take in the midst of a bunch of water? It's going to be a liquid. So the water, and this is kind of a weird one, but the water, hydrogen and oxygen molecules are very attracted to one, or hydrogen ions and hydroxide ions are very attracted to one another, and they form water, and it will be a liquid. And so we're going to have some spectator ions. It's not going to be the hydrogen and the hydroxide. We've got the first half of our overall ionic equation. We know that the sodium and the chloride stay in the same form. And that darned water comes right back out. As a liquid. So what are, and we'll just do this all on the same step, so this will be step 4 as well. What are our spectators? Fa-cha! Fa-cha! There's something so satisfying about crossing them off. Yes, ma'am?
Why do some of the things stay together and some of the things, why do the sodium and the chloride?
Okay, so our sodium and chloride, that's all soluble. So what we end up with for our net ionic is the formation of water. Okay, and that's our net ionic equation. So your quiz tomorrow is going to be writing some dissociation equations and predicting solubility, and then doing a couple, probably 2 of these the whole way through. Now, here's a question that always comes up that we haven't addressed yet. What happens if nothing, in fact, is insoluble? Let's do an example like that. So we've got ammonium nitrate and sodium chloride. Pretty common stuff. And first, of course, we would do our dissociation equations. NH4NO3 as a solid dissolved in water gives you NH4 1 plus and NO3 1 minus ions in aqueous solution. Okay, easy peasy. Copy, paste. And then sodium chloride, which, you know, geez Louise, haven't we done enough with sodium chloride? Well, it's pretty common stuff, you know, it's around a lot. 1 plus, aqueous, plus chloride 1 minus, also an aqueous solution. So now, if we're going to predict products for a double replacement reaction between these things, I'm actually just going to move this down. Move that down here. What would our predicted products be? Well, my money is on sodium nitrate and ammonium chloride. Sound right? Okay. Look up your solubilities for these. So we know that these things going in are all aqueous. What we don't know is the state of our products. So that's what we need to figure out. Who can tell me the solubility for ammonium chloride? Soluble! No Lone Ranger pencils for you boys, sorry. Well, what the heck? Everything's still soluble. What's going to happen here? We have a soup of ions. Nothing happens. It just stays a soup of ions. And the way we show this is that we do the overall ionic equation, and I'm going to again cheat and just copy and paste these. There's my product side. Guess what my reactant side, rather. Guess what my product side looks like? The same. Nothing changed. It's all still floating in just water. It's just ions floating in water. So what we typically do is we just write no precipitate. We can't write a net ionic equation. There's nothing to cancel out. There are no spectators. So you're done at step 3. You write an overall ionic and you say no precipitate occurs. Done. Can't promise that I won't give you one like that on your quiz. So, sometimes by accident. Depends on how late at night I'm writing them. Sometimes I screw up and I put something where everything's soluble. Surprise! And, you know, it's nice if I tell you that beforehand and how to handle that situation beforehand. So, okay, let's talk just briefly about ionization, and then we'll cut you out of here. We talked a little bit about ionization. We said that molecular compounds tend to ionize, and we talked about hydrogen chloride. So hydrogen chloride is a molecular compound, and it is a gas at room temperature. It is a gas you would not want to breathe. Guess what happens if you breathe hydrogen chloride gas? Huh? Well, not exactly. When it gets into your lungs, it mixes with water. That's the point at which it's hydrochloric acid. So you now have lungs full of hydrochloric acid. Not a nice way to die. You might in fact drown, I'm not sure, in your own tissues. They might start pumping water in to try to dilute it, and that might actually be the mechanism of death, but whatever it is, it's not pretty and it's not pleasant. So, if you put HCl into an aqueous solution, it will ionize. You get hydrogen ions and chloride ions. What we really get, though, and we didn't quite talk about this in the other example, I wanted to kind of keep it simple. The hydrogen ion is so attractive, it's never alone. You may have a friend like this. I had my best friend, you know, all through college, walking around next to her boy. Because not only was she never without a date, she was never without a line of people who wanted to date her. She was just amazing in every possible way. She was just like one of the best human beings I've ever met. Everyone just wanted to talk to her. That's the hydrogen ion. So, like, maybe you are that friend. I don't know. You can just slap a big H and a 1+ on you. You can show off your hydrogen ion status by walking around mostly naked with a plus sign on your belly, and only chemistry people will get the joke. That might actually drop the line back of people who want to date you, but, it'll really weed out the people who don't get the joke. So, hydrogen ions, gesundheit. Hydrogen ions in aqueous solution tend to get picked up by water. Because even though water's already paired up in neutral, it just can't resist a hydrogen ion. So what you get is what's called a hydronium ion. And if we were going on to the acid-base chapter, this would be extra important. We're not going to be able to get there, but let's just say that those hydronium ions figure very strongly in terms of what's an acid and what's a base. So when we put gaseous HCl, if we bubble that through water, what we really end up with is a hydronium ion and a chloride ion. And it's pretty nasty stuff. You don't want to come in contact with it, though it's not the strongest acid. Okay, this is a preview, actually, of Chapter 15. So we talk about the formation of hydronium as the hydration of hydrogen ions. What does it mean if you hydrate? What are you adding to yourself? Water. When we hydrate a hydrogen ion, we're adding water to a hydrogen ion. So, we are literally taking that hydrogen ion and adding it to a molecule of water. If you talk about it as the hydration of H1, this bullet point right here, this is important mostly because we're not going to get to Chapter 15, which is the acid-base theories. One of the things that I was least prepared for when I took college chemistry for the first time was dear sweet Dr. Kochnat, who I had for all of the general chemistry, would just toss off, well, then this is the proton donor, so it is the acid. I had no idea what he was talking about. Because hydrogen ions are basically, as I've said, just a naked proton. In one of the predominant acid-base theories, we talk about whatever gives a proton to something else, whatever donates a proton to the situation, is the acid. And that's that's Bronsted-Lowry definition of acids. We're not going to get to talk about that. Normally, if we had more time, we would do Bronsted-Lowry acid neutralizations. You would label the acids and the bases and the conjugates acid, blah, 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 all that. We're not getting there, so it's okay. But if and when you hear the term proton donor in a chemistry class later, that's what they're saying. It's giving up hydrogen ions. It's giving up protons. And it's giving them to somebody else, and that's what we define as the acid. Hydrogen chloride gives it up easily. So do all the other things that we think of as acids. Okay, so here's the cool thing, and this also explains something that we saw in a lab way back in Chapter 6. Electrolytes. So an electrolyte is something that when you put it in aqueous solution, it conducts electricity. You tested, well, we sort of virtually tested electrolytes using a little 9-volt battery and an LED, and, hey, does this work? Yes or no? The more ions that are floating in water, the more easily current is conducted. Okay? Stronger electrolytes have a better ability to conduct current. Anything that ionizes or dissociates is an electrolyte. So would sodium chloride be an electrolyte? Yeah, it dissociates. It's an ionic compound. Would potassium chloride be an electrolyte? Yeah, it dissociates. It's an ionic compound. Anything that ionizes. Would hydrochloric acid be an electrolyte? Yes, because it ionizes. It's not an ionic compound, but it's still an electrolyte because it ionizes. So back when we did the molecular versus ionic compounds, we had sugar, citric acid, and phenyl salicylate were our 3 molecular compounds. And the sugar does not ionize, does not dissociate, does not conduct. Salicylic acid won't even dissolve in water. Totally a moot issue. The citric acid, weirdly enough, though it's a molecular compound, it kind of conducts a little bit of electricity. Why? Have you made the connection yet? I'm not going to make it for you just yet. We'll go on, and I'll see at which point the light goes off. But just to mention that, yeah, the citric acid, even though it wasn't ionic, did conduct a little bit of electricity. Huh. Hydrogen halides, hydrogen plus a halogen. So you know this one, HCl, hydrogen chloride, also known as hydrochloric acid when it's an aqueous solution. Do any of the rest of these look familiar to you? Oh, somebody's looking at part of their ion Bible. That's a good thing to look at. Gee, what are all these things? What are they, Jeremy?
Well, the top one is hydrofluoric.
Hydrofluoric acid, hydrochloric acid. You want to take a guess on HBr? Hydrobromic acid. The bottom one's the weirdest one to say and the most fun to my lights. Hydroiodic acid. They're all acids. They're all binary acids. They're all soluble in water, and they all ionize. So has anybody figured out yet why citric acid conducts a little bit of current? It's an acid, and acids tend to ionize because they give up those hydrogens, they're proton donors. So basically, if it's an acid, whether it's acetic acid, carbonic acid, any of those, they tend to ionize. If it ionizes, it's an electrolyte. So all of these things, these hydrogen halides, are soluble in water and they ionize, but there's a catch. There's a catch. Did you guys read Animal Farm?
Yeah.
All animals are equal, but some are more equal than others. All of those hydrogen halides ionize. I probably completely muffed that quote. That's okay. 3 of them ionize completely. They are 100% ionized. Every single molecule of HCl, HBr, or HI ionize 100%. They are awesome electrolytes. They are what are called strong electrolytes. Well, we haven't mentioned who's not a strong electrolyte, but can you guess? Hydrogen fluoride, which actually makes a lot of sense. Fluoride is the most electronegative element there is. It's clinging to its little partner there, and the little electron that its partner brings to the party. So it doesn't ionize as completely. So it's what's called a weak electrolyte. Anything where most of it turns into ions is called a strong electrolyte. So for the most part, ionic compounds are almost entirely strong electrolytes. Of the binary acids, hydrochloric, hydrobromic, and hydroiodic are all strong electrolytes. So they conduct current quite well. Citric acid is a weak electrolyte. It doesn't ionize as completely as these guys. It's a weaker acid in general. You can, I don't know that you'd, well, actually, yeah, you could put pure citric acid on your tongue and you'd go, but you'd be fine. I actually have powdered citric acid in the back. You can go buy it at one of the Mennonite bulk stores and add it to your canned goods to make them a little bit more acidic. You can add it to a pie to give it a little bit of zing. You can, like elderberries. Who here has eaten elderberry pie? Elderberries are a very low acid fruit. And so when you make an elderberry pie, my grandma always added vinegar. You can add vinegar or lemon juice or powdered citric acid because your tongue likes it better if you have some tart to go with the sweet, and elderberries don't have a whole lot of tart. So anyway, those are the strong electrolytes, those acids. Not all acids are. Our citric acid conducts a little bit because it's a weak electrolyte. It partially ionizes in water. That, I believe, is where we're going to stop. And there. You knew it. You figured it out. You don't have to write this down if you want. But, you know, hydrogen fluoride does dissolve in water, and hydrofluoric acid is nasty, nasty stuff, but it still doesn't ionize completely. So it's still considered a weaker electrolyte. That's it. Tomorrow, a quiz on writing net ionic equations. So doing dissolution equations, predicting solubilities, writing net ionics. Probably a bonus question on the ionization with acids. Because we didn't really spend much time on it. And then we'll turn in our books and we'll make ice cream. And I'll post your final assignments to Classroom, so you will need your phones tomorrow. They're easy, don't worry. It's a checklist of items you have to complete before I let you off the hook for the year. So one of the checklist items is like turning in your book. So it's typically a 4-point checklist. You get all 4 of those things done, and then I'm done with you. So questions, comments, concerns? Cookies. Okay. Cookies? Cookies and cream ice cream?